this program, we're going to go a long way away and look at the very early universe. But first, it's been suggested that we might begin our Sky at Night programs with a very brief look around the sky. And I think that's rather a good idea. So here goes. And of course, we're still dominated by Mars, which has been as close to us as it can ever be. 34.5 million miles. It's still very bright, brighter than any other star we can see, and it's there, shining down from the faint stars of Aquarius. And even with a small telescope, you can see the surface details, and we've had some really good pictures. Here's one taken by Jamie Cooper. There you see the white polar ice cap, the red deserts, and the dark areas. Also one here by Martin Mobberley. Again, a splendid view. And from Ireland, Peter Paice. And all those show a good deal of detail with small telescopes, but we also used the Hubble Space Telescope. And that took advantage of Mars being so near and took this picture on the day of closest approach. And there you see Mars in real detail. Though, of course, to see the giant volcanoes in their form, we do need space probes. Also, both Martin Mobberley and Mike Tyrrell have produced animations from their various observations, and these are really quite striking. Well, Mars is there. It'll remain bright for some weeks yet, so have a look at it. And we're going to have a competition. So if you've taken or are going to take photographs of Mars, do let us have them. Send them to Sky at Night, Mars Photos, room G06, BBC Birmingham, B57QQ, or email them to www.bbc.co.uk/space, and we'll show the best ones in our next program. And now for the stars. First of all, two very bright stars to either side of the pole star at about the same distance from it, Vega in the west and Capella in the east. You can't miss those. And the main autumn constellation is Pegasus, the flying horse, now high up in the south after dark. The four main stars make up a square. In mythology, Pegasus was a flying horse, was not much like a horse here. And the stars in the square are easy to find, even though I think maps make them look rather smaller and brighter than they really are. But look at them carefully. The upper right-hand star, called Sept, that is orange, the others are white. So that orange star has a lower surface temperature. And well below the square, almost on the horizon, you see the bright star Fomalhaut in the southern fish. And that's interesting, not much more than 20 light years away, and it may possibly have a system of planets. We can't be sure, but certainly it's a pretty good candidate. So those are some of the things you can see in the sky now. And so now, on to our main theme, and welcome back to Dr. Carlos Frenk. Welcome back, Carlos. Now, I know you've just come back from a very important conference about the very early universe. What did that bring up?
Well, this was a big conference in Sydney, Australia. This is the General Assembly of the International Astronomical Union that happens every 3 years. And I never really ceased to be amazed at the breathtaking progress in the subject. One of the exciting developments that were reported at the meeting was the realization that astronomers have now been able to carry out a very detailed census of the contents of the universe, not only of the universe nearby, but also of the very early universe. We now have a very detailed inventory of what the universe contained about 3,000 million years after the Big Bang.
And when was the Big Bang?
Well, the Big Bang happened, we now know, almost 13.5 billion years ago. That's 13.7 thousand million years ago.
And how did the Big Bang originate?
Well, that I think it's still a question that lies beyond the boundary of our current understanding. But we cannot go to the Big Bang, but we can get very, very close. We can get almost as close as you might wish. In a tiny fraction of a second after the Big Bang, I think we already have glimpses of what probably happened there. But the moment of the Big Bang, how the Big Bang happened, is still beyond the frontiers of the current understanding of physics.
Right, the Big Bang has happened. What next? Inflation?
Well, soon after the universe began, we believe that the universe underwent a very traumatic episode where it grew very fast, very rapidly, in the phenomenon that we know as cosmic inflation. Now, the reason we have reason to believe that this happened is because the consequences of inflation are here to be seen. During the moment of inflation, or the very brief period of inflation, the universe acquired small irregularities. They were all imperceptibly small. But these irregularities, after the period of inflation, grew. They left an imprint in the heat of the Big Bang, what we now see today as a microwave background radiation. We see these imperfections as tiny little ripples, which are very, very small, yet large enough that they can be detected.
What equipment is used for this?
Essentially, radio telescopes is what is used to study this microwave background radiation. It can be studied from the ground, but the best place to examine this radiation in detail is from outer space, away from sources of interference. And there have been a number of satellites that have been used for this. In particular, 10 years ago, NASA flew what became a very celebrated satellite, the COBE satellite. Yes, COBE stands for Cosmic Background Explorer Satellite, which took the first image of the heat left over from the Big Bang, an image that took us back to when the universe was a mere 300,000 years old, which is the human equivalent of one day.
Well, of course, there were no galaxies then. In the very early universe, they hadn't formed.
They had not formed. The galaxies were to grow later as the small irregularities grew inexorably under the force of gravity. As the universe evolved, these small irregularities became larger and larger until they were no longer capable of expanding with the rest of the universe, and at that point they collapsed and formed an object. They gave rise to protogalaxies, to small objects, subgalactic fragments consisting of a mixture of dark matter and gas. The rotating gas settled into a disk and subsequently fragmented into stars in these small subgalactic objects, which were then drawn together by the force of gravity and then began to collide with one another, building up larger and larger structures in what astronomers like to call a hierarchy of structure formation. This process is hierarchical in the sense that the small first objects are formed, the objects that form first are small, and then through this process of merging and fusion, larger and larger galaxies are built.
What about this latest satellite, WMAP?
WMAP studied the microwave background radiation again, but now with much more sensitivity and in particular much better resolution than COBE. And the results from WMAP, which were also discussed at this meeting I was at in Sydney just a few weeks ago, those results are absolutely astounding. They are fantastic. We have now a pristine image of the early universe, because that's what these satellites do. They take images of the early universe. And what is absolutely astounding is that the nature of these small irregularities is exactly what physicists had predicted should be there 20 years ago. Physicists made these predictions 20 years ago, and there they are, corroborated in nature.
We hear a great deal now about the dark ages of the universe.
Yes, just after the universe allowed us to have a glimpse of what was happening at early times through the emission of the heat of the Big Bang, the microwave background radiation, just as that happened, the universe closed down on us again, because very dense and opaque clouds of gas formed, and they absorbed all the radiation of the universe, causing the universe to go through what has been very correctly known as the Dark Ages. It's a period that lasted about 1,000 million years. Eventually, the Dark Ages came to an end when the first quasars stuttered into life, and the radiation produced by the first quasars and the first stars burnt out these clouds, allowing the light to shine through, and at that point the universe erupted into light as millions and millions of stars began to form.
Well, for a long time, quasars were a real mystery, but we now know what a quasar is.
I think we have some understanding of why quasars shine. The quasars are fantastically energetic phenomena which we believe are triggered by the presence of a supermassive black hole in the center of a forming galaxy. This black hole eats up essentially gas from its surroundings, and when the gas falls into the black hole, just before it falls in, it liberates enormous amounts of radiation which make these quasars shine. And we now believe that the quasar phase is an integral part of the formation of a galaxy. It's quite likely, in fact, that all galaxies may have gone through a quasar phase earlier on.
It's always struck me being significant that there are no quasars anywhere near us.
Well, that is probably just one of these accidents of that might happen. You might go in the motorway and you don't see a red car for quite a while. That doesn't mean that there aren't red cars. You just don't see them at a particular time. It is true that the quasar population today is declining. The quasars had their golden era when the universe was about half its current age, roughly 6 or 7,000 million years ago. That's the era where the quasars were dominant, and but the population's been dwindling since then. Not because the black holes aren't there, simply because all the gas that's needed to fuel the quasars is being consumed in formation of stars. And so there's less and less gas available to feed these hungry monsters at the centers of galaxies.
Do you think our Milky Way galaxy ever went through a quasar stage?
I think it did. I think we now know from a variety of observations in the sub-millimeter region made in the last few years that around Milky Way galaxy harbors a very massive black hole in its center. It's a black hole with a mass of about 1 million times the mass of the Sun, and which probably caused our own Milky Way to shine as, if not a quasar, what we call an active galactic nucleus, which is just a small version of a quasar some billions of years ago. So I think it's almost certainly the case that our own Milky Way was once something resembling a quasar.
I imagine in those early days, when the universe was smaller than it is now, there were good many collisions between galaxies.
Yes, indeed. In fact, we believe that collisions are one of the major mechanisms by which galaxies, the galaxies that we see today, grew to their present size. As the universe emerged from the Dark Ages, matter congealed into small clumps, much smaller than galaxies, what we might want to call proto-galaxies. These small fragments were drawn together by their mutual gravitational attraction, eventually colliding and fusing to make ever larger objects. This process of galaxy fusion and merger, we believe, is what led to the big galaxies that we see in the universe today. So most of the galaxies in the universe today, we have experienced merger events such as those that the computer simulations reveal would have inevitably happened if the universe was the way we believe it was from the information conveyed to us by the microwave background radiation.
We can look back now to the very early universe with the Hubble Deep Field and see what it was like and it's very different now. And we can really follow the evolution right the way through.
Yes, the Hubble Space Telescope completely revolutionized our view of the early universe 6 or 7 years ago, when, in fact, as one of the rare examples of collective scientific enterprise, the Hubble Space Telescope pointed this very expensive instrument at a small patch of sky for a long period of time and then made the data available to the astronomical community at large. And this small image called the Hubble Deep Field completely revolutionized our way of thinking about the universe, because this image was so deep that it revealed galaxies so distant that the light has taken most of the age of the universe.
About 12,000 million years, something like that?
About 12,000 million years for the most distant ones. And we are beginning to understand finally the processes that took our early, uniform, simple universe into this fantastically complex and structured universe that we see today. And it is the laws of physics that allow us to follow this fantastic story as it unfolds.
Of course, we can see collisions between galaxies now.
Yes, here we see two galaxies approaching in a computer simulation of a merger, and now they feel the disruptive effects of each other. They execute a cosmic dance, and then they fall back. They are now entering the process of merging. The galaxies now resemble the mice. Now they look like the antenna. And eventually, the two galaxies disappear, giving rise to a single object.
We can see that, can't we? I think like the tadpole and the antennae.
We see that happening today. And
tadpole's lovely, I think.
The tadpole is a fantastic galaxy.
What's happening there?
We caught the galaxy there in an act of naked cosmic cannibalism, a big galaxy eating a small galaxy. I think the small galaxy passed by the big one captured it through the force of gravity, and what we see there is the small galaxy being torn apart before it gets eaten and digested by the big galaxy.
Then we have the mice. I love that name.
Yes, the mice is a much more spectacular version of this fusion or merger event, because here, unlike in the tadpole where there's a big galaxy eating a small galaxy, here we have two similar-sized galaxies that have come together under the force of gravity, and they will eventually fuse or merge together in what would really be a spectacular event accompanied by a massive burst of star formation and the generation of copious amounts of X-rays and UV radiation.
I think, though, the most spectacular of the lot are the antennae galaxies, that lovely Hubble picture of them.
Oh yes, they're fantastic. There you see a merger almost near the final stages. You see the two galaxies now very close together, ejecting these streams of gas and stars that we call tidal tails, which give them their characteristic appearance. And it's very likely that our own Milky Way indulged in a spate of galactic cannibalism like this one. For example, one of the side effects of this phenomenon is the creation, the formation of globular cluster, which are small objects, piles of about 100,000 or million stars, of which our Milky Way has about 100 examples. So
we have some good ones here, one or two on view now.
Yes, absolutely, and they can be seen just with binoculars and admired in their fantastic beauty, little beehives of stars, and they seem to be formed when acts of galactic cannibalism happen. And so it may well be that the globular clusters in our own Milky Way are the remnant of a digestive episode that our galaxy indulged in several billion years ago.
Well, we are now swallowing a small galaxy, aren't we? Sagdig.
We are, indeed, and we see also what we call tidal debris, bits of the galaxy that get torn apart as the galaxy is being eaten up by our own Milky Way. That's a very small galaxy, and I think our galaxy has digested several of these small neighbors or satellites that venture too close to where the action is happening.
But, of course, Andromeda Galaxy, more than 2 million light years away, coming towards us. I gather there will be a collision between Andromeda Galaxy, which you can see in the night sky now, and our own.
It's inevitable. Just as night follows day, the Milky Way and the Andromeda Galaxy are destined to collide. They're already approaching one another under the influence of gravity, and when the two galaxies come together in a very spectacular episode that will be accompanied by a massive burst of stars. And
I imagine the actual stars won't collide very often. They're so widely spaced, but the interstellar matter will be colliding all the time. It'll be total chaos. When will this happen?
Well, fortunately, there's no cause for alarm. This will not happen for another 10 billion years, 10,000 million years or so into the future. So there's no cause for alarm, but just as night follows day, the two galaxies will collide and the two galaxies will fuse, and the result will be not a beautiful spiral galaxy like the Milky Way, but these other rather ordinary looking galaxies that we call elliptical galaxies, essentially amorphous piles of stars, which are the remnants of these spectacular merging events.
At least by that time, our Earth will no longer exist. It will have been devoured by the sun.
It would have been devoured by the sun, indeed, and the sun itself by then will probably have already reached the end of its life by consuming its nuclear fuel. It'll be a dark remnant. So our galaxy, when this happens, will not look anywhere as nice and beautiful as it looks today.
And in some way, the universe is a violent place.
It is in many ways, but it's also a beautiful place.
Well, now you're still looking back at the very early universe. What are the next stages of research?
Well, even though we're beginning to patch together all these events, there's still a huge amount that we don't know, and there's enormous gaps in our understanding, and fortunately the ingenuity of mankind has no limits, and there are a number of new developments in terms of new telescopes which will undertake surveys of the early universe, new satellites. For example, the European Space Agency is planning to launch the Planck satellite in around 2007 or 2008 that will look at the microwave sky, at this heat left over from the Big Bang with unprecedented detail. NASA, and in collaboration with the European Space Agency as well, are planning to launch a futuristic version of the Hubble Space Telescope, the James Webb Telescope, which I think the latest is that it will be launched in around 2010 or 2011, and that will allow us to peer right the way back to the very beginnings of the universe.
And I wonder, will you ever get back to the very beginning? I don't know. One day I suppose we may, but I think not yet. Anyway, we're learning more all the time. That's all tremendously exciting.
It is indeed.
Carlos, thank you so much.
Thank you, Patrick.
I wonder if we ever know the full truth. When I come back next month, we're coming much nearer home, right into the solar system, and talking about the giant planet Jupiter. So until then, good night.